Okay, hello again. In the last video, we talked about the importance of the idea of limit in calculus. So we're going to continue in this video with chapter 2. Again, I hope you're doing well. So let's start working on the idea of limit. So I'm going to go back to where we left off last time, which was about right here. Right here, right here. All right, so the idea of the limit has to do with the function values, behavior of the function values when the input values approach a number. The notation for it is this notation right here. So the way we read it is limit of f of x when x approaches 2 is 1. Again, limit of f of x when x approaches 2 is 1. That's how we read it. So the idea is when you are around 2 right here, when x approaches 2 right here, now not at 2, we don't care what's going on at 2, but when we approach 2 from left and right, the function values, right, are right here, right? So these are the function values. So what is going on with the function values? Well, as I approach 2 from right, the function values approach 1, right? And when I approach 2 from left, well, the function values are right here. So what do? Well, they approach 1, right? So that's the idea of a limit. When the input values approach a number, how do the function values behave? They approach a number or not? If they approach a number, when the input values approach this number from left and right, then we call that the limit of that function. Okay? So let's talk a little bit more about this. So now, again, we don't care about the value itself at a. So the function maybe is not even defined at a. We just care about what happens to the function values when you approach input values from right and left. Of course, in calculus 1, the input value is only one variable. So in calculus 3, when you talk about multivariable calculus, the input value could be more than one. So when we talk about a point, we're talking about two-dimensional or three-dimensional or many-dimensional approaching a number. But here, this is the same idea, as I said before. All of these ideas can be extended to more than one variable. For now, we're talking about only one variable, right? So if I approach a from right and left, what happens to the function values? That's the idea. So when we say the limit is L, that means if you're on the x around a, then on the y-axis, the y values are around L, right? The closer you are to a, the closer the y values are to L. That's the idea. All right, so one way to figure out what the limit of a function is by just looking at the function values. Where are the function values? Well, let's do it with a calculator. So with the calculator, we are going to put this function in the calculator. So it's x squared minus 4 divided by x squared plus x minus 6. Okay, now I'm going to go to the table, set up the table, second table set. And I'm going to make that number be the number that I'm approaching here, 2. So I'm going to start the table at 2, and I'm going to go to numbers close to 2. So I'm going to pick a step. So here is 2, right? So here is 2. So I'm going to pick a step and go to the right of 2 and go to the left of 2. And in the table, I'm going to look at the function values, what they do. So I'm going to pick that really small step, and I'm going to make this auto. So the calculator would create a table. So I go to second, table. So calculator creates a table for me. And notice that you can scroll up and down and you see a bunch of numbers here. In fact, you could go up and down forever, and then calculator just gives you values. So these are the input values. 3 input values to the left of 2 and 3 input values to the right. And the step, the increment is 0.01. And look at what the function values do. It looks like they're approaching a number. And that number is what? That number is, looks like 0.8, right? So we say that the limit is 0.8. Okay, so that's one way to find the limit. Let's look at another example. In this example, again, we are given a bunch of numbers to use. We could do that, but I'm going to do it just automatically. I'm just going to go close, just like I did for the other function. Now for this function, since it's a trig function, right, I'm going to change the function to trig function. Now for trig function, you have to watch your mode. Make sure your mode is in radian, and then put the function there. So the function is sine of 2x divided by x, right? You don't need a parenthesis here because calculator, when you close this, calculator considers that to be the numerator, and divided by x. Then we can set up the table. If you want to put specifically these numbers in the calculator, you could do that. You just have to change that to ask on the table set, and then go to table, and there's nothing there. So what you can do is you can put these numbers there. So I want to start from 0 and go to the right of it, 0.1, 0.01, 0.001, right? So I can start from maybe negative 0.1, negative 0.01, negative 0.001, right? And so forth. And then to the right of it, I can start from 0.001. Oops, did something wrong. What did I do? I put 2 decimal places. 0.001, 0.01, and then 0.1, right? So now, of course, these are, in the calculator, there are 2, but they're not 2 because the calculator doesn't have room to put all the decimal places. The reason you see it here because I changed the mode to like 4 or 5 decimal places, so the calculator shows them. But here it doesn't, and this is automatic. I wanted to do it this way so you see how it is done by hand, manually, instead of auto. Okay, so that you see that as I go to the right of 0 and approach it, these numbers, they're approaching 2. And if I go to the left of 0 and I approach it, these numbers are approaching 2. So from left and right, looks like the numbers are approaching 2. So the answer is 2. Later we're going to learn how to do this without the table, just algebraically, using trigonometry and algebra, but for now, this is the way we find the limit. All right, so we're going to also define limits that are one-sided. That means sometimes here is a, and we care about the function values when we approach a from the left. So we don't care what's going on the right. We just care about this part. So if that's the case, then we write the limit this way. We write limit of f of x when x approaches a from left. Now, of course, somebody could have done just put left on the top, but they didn't like this notation, so you come up with this notation. A with a minus on the top. It means approaching A from left. That doesn't mean negative A, right? Alright, so here's an example of left limit. What's the limit of f of x when x approaches 6 from left? So here's 6. We're going from the left of 6 this way. So basically means these values, right? And these values have y values up there, right? Where are the y values? Well, they're right there, right? So it looks like they're approaching what? They're approaching 2, right? So the limit when we approach 6 from left is 2. What about negative 8 from left? Well, negative 8 from left means we're over here, right? And if you think of function values here, it's kind of hard to draw a straight line here, but the function values looks like they're approaching what? They're approaching negative 6, right? So the limit of f of x when x approaches negative 8 from left is negative 6. All right. Now, what about if we are interested in the behavior of the function when input values approach a from right? Then the notation is x approaches a from the right. So we put a plus sign on the top. And an example of that is the same example, but this time from the right. What's the limit of f of x when x approaches 6 from right? So from right means we are right here, right? And these function values are way up there, right? So it looks like they're approaching what? They're approaching 5, right? And what about negative 8 from right? Negative 8 from right, we're over here, right? So those function values are again over here, right? And those function values looks like they're approaching negative 6, right? All right. Now, how do we relate this two-sided limit? This is a two-sided limit here. This is a two-sided limit, and these are one-sided limits. So, if the one-sided limit from the left and from the right are the same, they exist and they're the same, then we say that two-sided limit equals to that number. So if and only if is a way to say that if the left side is true, then the right side is true, and if the right side is true, then the left side is true. If and only if means this. If you just put if, so if you put if A then B, something like that, then that's one-sided. So here we have a two-sided statement. So that means in order for two-sided limit to exist, the one-sided limits, both of them have to exist, and they have to equal to the same number, right? All right, so let's look at an example here. Is it true that the limit of f of x equals to 5 when x approaches 6? Well, let's see. If you go from the left of 6, right here, from the left of 6, looks like the limit is what? From the left of 6 is 2, right? Because these are the function values, and looks like the function values are approaching 2, right? If you go from the right of 6, which is right there, then we are up here, and looks like from the right, the function values are approaching 5. So no, this is not true, because the two limits are not the same. So we say that limit of f of x when x approaches 6 does not exist, D and E. Okay? All right, so we could also talk about infinite limits. What does that mean? It means that we have a situation that when input values approach a number in the domain from left or from right, right, then the function values go to infinity. For example, when x approaches a from left, you can think of a situation like this. When this is a, and when you approach a from left, the function goes to infinity, like that. Then if that is the case, we say that the limit is positive infinity. That doesn't mean the limit exists. It just means that it goes to infinity. What about from the right? Well, from the right, you can think of it if you approach a from the right, then the function goes to positive infinity. Then we have this case here. And then what about if it goes to negative infinity? Well, we could have that where a is here, and then the function approaches negative infinity from the left. And then over here, from the left approaches positive infinity. Negative infinity, but from the right. Okay? So all of these are different types of limits we can encounter in calculus. Now, what about these? Well, here is two-sided limit. So the only time that we write the two-sided limit equals to infinity is when we have a situation where the limit from the left is infinity positive and limit from the right is also infinity positive. If that's the case, then we write that the limit is positive infinity. Also, if the limit from the left and the right is negative infinity, like this, then we write the limit is negative infinity. Now, again, this doesn't mean that the limit exists. It just means it goes to infinity. Okay? Okay, so let's look at some examples. From the here, this is actually a -1 here. So it has a vertical asymptote at -1. Okay? You can't see it here, so I can graph it. So notice that when I go to -1 from the right, the function goes to positive infinity. And when I go to -1 from left, it goes to negative infinity. So what do we say about this limit? What's the limit of f of x when x approaches -1? Well, since the left and the right limit are not the same infinity, we say that the limit does not exist. Okay? Now, what about in this situation here? When limit of f of x when x approaches -2 from right is negative infinity, and from left is also negative infinity. So in this situation, we can say the limit is negative infinity. We don't say it does not exist. We say it's negative infinity. Why? Because the left and the right limit go to the same infinity, so we say the limit is infinity. But that doesn't mean the limit exists. It means that the limit goes to infinity. Okay? All right. So if we have a situation where the function at a, right, so here is a, if the function from the left goes to infinity, positive or negative, or on the right goes to positive or negative, any of these, if any of these is true, we say that x equals to a is a vertical asymptote. In algebra, we didn't define vertical asymptote this way. We defined it differently, but here we define it this way. So here's an example. So what is the limit of f of x when x approaches -3 from left? Well, we know that if I put a -3 here for x, the denominator becomes 0. So that means 1 over 0 equals to infinity. But we don't know which infinity. So let's figure it out. So here is -3, and this limit is from the left. So we're going to pick a number really close to negative 3. Let's say negative 3.1. And then we are going to substitute it here for x. Negative 3.1 plus 3 is negative 0.1. And negative 0.1 to the fourth power is a positive number. So I know this goes to infinity, but what infinity? Positive. So this is positive infinity. Now what about from the right? Well, we're going to pick a number to the right of negative 3. Let's say negative 2.9. Now, negative 2.9, we substituted here for x again. This time is negative 2.9. Negative 2.9 plus 3 is 0.1 positive, and 0.1 positive to the fourth power is a positive number. So that is also positive infinity. That means this limit is positive infinity, and that means that x equals to negative 3 is a vertical asymptote for this function, right? So let me erase everything here. You can see it. Okay? All right. Here is another example. Here is the graph. Again, you see the limit when x approaches negative 2 from the right here is negative infinity. From the left is also negative infinity. So we can say this is negative infinity, this is negative infinity. And what about 0 from the left is negative infinity, right? You see that? Goes to negative infinity. From the right of 0, it goes to positive infinity, right? All right, now, so this proves that x equals to negative 2 is a vertical asymptote, and x equal to 0 is a vertical asymptote, right? All right. So what about these from the graph? Well, we can easily see that when x approaches 3 from right, this goes to positive infinity. When x approaches 3 from the left, this goes to negative infinity. And we know that this does not exist, right? And again, it proves that x equal to 3 is a vertical asymptote. All right? All right, so let's talk about application of this. Albert Einstein has an equation that relates the mass of an object that is moving to mass of an object at rest. You see, my car that is parked in the parking lot has certain mass. As soon as I start moving, I start driving it, the mass of the car actually changes, believe it or not. And it changes according to this equation. Now, velocity of the car with respect to velocity of the light, which is 300,000 kilometers per second, or 180,000 miles per second. Now, compared to that, that is the velocity of my car is almost nothing. So this denominator really is just 1, so that it's very close to 1. So the change of mass is so small that you can't even detect it. But when the object starts moving faster and faster, that means when the velocity of the object approaches the velocity of the light, then what happens here? Well, let's say v is c. Can v be c? No, because if v is c, then that would be c squared over c squared, which is 1. And 1 minus 1 is 0. Square root of 0 is 0. Denominator is 0. No, can't have that in mathematics and in physics. In fact, one of the ways you can figure out whether a theory makes sense or not is to look at the equations and see if you find denominator of 0. So that means v cannot be c, but can v approach c? Yes. And what happens if we do that? Well, let's see. To make it easy for our limit procedures, we are going to change this to, first of all, we're going to divide both sides by m sub 0 and get rid of that m sub 0 on the right. And then we're going to make v squared over c squared v over c to the second power. And we're going to take v over c and let it be x, right? So now we just have this, which is that function right there. Now, when x approaches 1 from left, because v cannot be more than c, so we can't go to the right. So when x approaches 1, actually v approaches what? C, right? In other words, for x to approach 1, v has to approach c. And if that happens, then this limit is going to be infinity and looks like it's positive infinity, right? So that means that as the speed of the object goes to closer and gets closer and closer to the speed of light, the mass of the object gets infinite mass, right? So that means you cannot go with the velocity of light, basically, from rest, right? You can start from rest and accelerate to the velocity of light. It's just not possible. Can things go faster than speed of light? Yes, if they don't start from rest, right? All right, so let me talk about this idea of the speed of light. It came actually from Maxwell's insight. Maxwell's equations, you learn them in Calculus 3, but Maxwell's equations give us this relationship between velocity of what Maxwell was working with, which was basically a combination of electric and magnetic fields. So what he realized was that the velocity of the thing that he was working with was related to these two numbers. And these two numbers are called the mu naught, or mu sub 0, is called the permeability of a space, which is the resistance of free space to formation of magnetic field. If you want to create magnetic field in space, in free space resists that, and that resistance is given by this number right here. Now, epsilon naught, or epsilon sub 0, is the resistance to the formation of electric field. If you create electric field, the free space resists that, and that number is given by this right here. Now, he realized that the velocity of what he was working with was equal to square root of 1 over this product. Now, the units of these two numbers are given by, these are, again, the units in physics, Weber over amps times meter, and coulombs squared over Newton times meter squared. You probably know Newton and meter and maybe Coulomb in physics and Weber. But I'm going to show you what he did. So what he did, basically took those numbers and put them in this equation and did the unit analysis. Now, if you do the unit analysis, Weber is that, you can search it in internet and find, or in physics books. This is Weber, and this is amps times meter, and if you multiply them, multiply these two units, you end up, and put it in this under a square root, you end up with meter per second. So he discovered that whatever he was working with had a velocity of 299,792,251.8 meters per second. Now, what moves that fast? Well, he knew about James Bradley's estimate of the speed of light. So he found a way to measure how fast light moves using mirrors and things, okay? But that itself is pretty tricky. You can actually search that and see how he was able to find the estimate for velocity of light. But that was what Maxwell knew. So we said, okay, well, look, maybe what I'm working with is light. So he was the first person who came up with this idea that light, visible light, basically is nothing but combination of what? Of two fields, magnetic and electric fields. Now, in the notes, if you click on this picture here, it takes you to this website that you can watch that video, like 15-minute video on this idea. I took the numbers because I wanted to talk about the speed of light. So that's the speed of light. And it is constant. It's not constant, but it is the speed limit when you start from rest, because these numbers stay the same for free space. So in free space, you have a speed limit. That's the speed limit. You cannot go faster than the speed of light. Okay? So that's the idea. All right, so let's talk about the limit laws, which are pretty easy. Limit laws tell us that if you want to take the limit of a sum of two functions, that would be the sum of the limits. You see, it makes sense? Limit of a sum is the sum of the limits. Limit of a difference is the difference of the limits. Now, we can use these laws only if the limits of those functions, right, are actually I just saw a typo here. I have to fix it. So let's fix it together here. There you go. That should be f of x, and that should be g of x. There. All right. I'll move this over here. Okay, so limit of f of x and limit of g of x have to be they have to exist. If they are, then we can use these limit laws. So limit of a number times a function is the number times the limit of the function, right? Limit of a product is the product of the limits. Limit of a quotient is the quotient of the limits. Of course, the denominator can't be zero. Limit of a function to a power is the limit of the function to that power. Limit of a nth root of a function is the nth root of the limit of the function. Now, of course, if n is even, inside cannot be negative. If n is odd, then the limit could be any number. All right, so here's an example. Basically, we don't do that when we find the limits. This is just to understand that the reason we can do it is because of the laws, these limit laws, right? So limit of this is basically limit of a sum is the sum of two limits, and limit of negative 2 times x is negative 2 times limit of x, and so forth. Okay? And this one, we have limit of f of x is that, limit of g of x is that. So we evaluate it. And now here, limit of x, of course, is just, we know limit of x is the function x, and when x approaches 1, the limit, of course, is 1, right? And limit of 5, limit of a constant y equals to 5 is just that. And if you go to 1, the limit is just 5, right? From left and right. So that's how we know all of these. Okay, so if limit of f of x is 8 and limit of g of x is 4 when x approaches 1, then what's that limit? Well, that limit would be, this limit is when we substitute these, right? First, we use the limit law. What's the limit of the square root of something? What is the square root of limit something, right? So we put the limit inside. And then what's the limit of a product? Product of the limit. What's the limit of a sum? Sum of the limits, and we get an answer. Easy stuff, right? All right. So limits of polynomials and rational functions are very easy to find. You just have to find the function value. So limit of a polynomial is nothing but the function value. Why? Because polynomials are basically don't have any breaks. So at any given point, if you want to find the limit, if you go from left and right of this number, well, obviously you go to that number. The function values approach that number, and that is the limit. So you just substitute. For rational functions do have vertical asymptotes, horizontal asymptotes, and all that. But if you're within the domain of the rational function, the answer is just by substitution, is the function value at that number. So that makes it easy to find the limit of polynomial and rational functions. Just substitute, right? So we just substitute 3. 3 is in the domain, so we can just substitute and get the answer, right? And I'll let you check that out. Just stop the video if you want to look at it. All right. So what if the substitution doesn't work? Well, we have to kind of modify the expression we get. Now, one situation when substitution doesn't work is when we get something like 0 over 0. And 0 over 0 is a situation like, let's say we have a situation like this. When x approaches 1, if you substitute, you get 0 over 0. But if you cancel these, right, then you don't get 0 over 0. So the trick is to get rid of what causes 0 over 0 in the structure. And whatever is left over after we cancel what causes 0 over 0 is easy to find the limit because we can just substitute. So let's look at some examples. So if we have polynomials in the numerator and denominator, we can factor them. If we have expressions involving the square root, we can multiply by conjugates to get rid of the square root. And if we have complex fractions, we can simplify them. So let's look at some examples. So here's an example where if you substitute, we get 0 over 0. So what do? We factor. Now to factor this polynomial, of course, you can just write it as what? Write it as 3 times 2 factors like that. And just put the roots of that polynomial there. So what are the roots of that polynomial? Well, that would be 7 plus and minus the square root of 49 minus 4 times 3 times 2. That's quadratic formula divided by 6, right? So that is 7 plus and minus 5, because that's 49 minus 24, which is 25. The square root of 25 is 5, divided by 6. So either we get 7 plus 5 divided by 6, which is 2, or 7 minus 5, 2 over 6, which is 1/3. So we're going to put them here, 1/3 and 2, right? Now, if you multiply by 3, the first factor, you're going to get that. So that's the factor. And now, can we cancel this with this? No, because this one is t minus 2, this is 2 minus t. Now we use the identity that a minus b is the same as negative b minus a. Right? So instead of 2 minus t, I can put t minus 2 if I put the negative here. Now we can cancel these. So what do we end up with? We end up with the limit of 3t minus 1, but there is a negative here because the negative is left over in the denominator. And when t approaches 2, what do we get? Well, we get negative 5, right, if you substitute. That's the way we deal with this situation. What about here? Well, here we have to get rid of that square root. The trick is to multiply by conjugate. What do I mean by conjugate? Well, we use this idea that a minus b times a plus b equals to a squared minus b squared. Now here we're going to assume that this is capital A and this whole thing here is capital B. So we're going to multiply by what? Multiply by a plus b, and a plus b in the numerator and denominator. Now, how does that help? Well, it gets rid of that square root, because square root to the second power would cancel. So we're going to get just the inside of the square root, right? Denominator, don't multiply it out, because we are hoping we get something in the numerator to cancel something in the denominator. So you shouldn't multiply out the denominator. You need to wait until you finish simplifying the numerator, and somehow magically you get something that cancels. Well, it's not magic, of course, it's mathematics. So you get these and they cancel. So what we end up with is the limit of 1 over a plus square root of a squared minus x squared when x approaches 0. And if I put a 0 here, I get 1 over a plus square root of a squared. Square root of a squared is a, because a squared is a positive number. And a plus a is 2a, so we get that. So that's the answer. All right, how do we deal with that? Well, it's a complex fraction, so we're going to simplify it. Now, notice that we cannot use limit laws. If we substitute, we get 1 over 2 minus 1 over 2 over 1 minus 1, which is 0 over 0 again. Doesn't work. So, even though all of these are what? All of these have limits and we can substitute and find them, but it doesn't work because you get 0 over 0. So what do? We multiply the numerator. So we have to multiply the numerator by 2 times x plus 1, and then denominator also with 2 times x plus 1. That's what we have to do. When we do this in the numerator, it gets rid of the fractions, and then denominator, we keep it like that. So here you go. So what we get is this right here. So 2 times x plus 1 times 1 over x plus 1. X plus 1 goes away, we can just get 2. And then 2 times x plus 1 times 1 half. The 2's goes away, so we get negative x plus 1. Denominator, we keep it. Remember, you don't multiply out because we're hoping we get something to simplify the denominator. So we're going to wait until we get simplified numerator. Now, looks like this is 1 minus x. This is x minus 1. So we can write this as x minus 1 if you put a negative before it, right? So this goes away, x minus 1 goes away, so we get negative 1 over 2 times x plus 1. Now we substitute, we get the answer. All right. What about this one? Well, in this case, we are not going to be able to use the limit laws. Why? Because this limit doesn't exist. When you substitute 0 here, it doesn't work. And here either. So that means limit laws don't apply here. Because remember, the condition to use limit laws is if the limits actually exist. And here they don't exist. So what do we have to do? We have to simplify it. So how do you simplify it? You just combine the fractions. How do you combine the fractions? You make the denominators the same. What is the common denominator? X times x minus 5. So here you go, the denominators are the same now. Now you write the denominator and add the numerators. And again, mathematically, we get magic here and they cancel, so we get 1 over x minus 5. When you substitute 0 here, you get negative 1/5. Okay, you can look at it. You can stop the video and look at it. But I'm going to move on to the next one, which is a piecewise function. So what's the limit here? Well, remember, the limit, we can go from left or right. If I go from the left of 2 and find the limit, this piecewise function has this piece. And if I go to the right of 2, I have to use this piece. So let's do that. So limit from the left, we use the top one, and we get 5. Limit from the right, we use the bottom one, and we get that. Are these the same? No. So that limit does not exist, because the left and the right don't equal. They exist, but they are not equal. And we didn't need the graph to find the limit, but this is the graph. And you obviously see the left and the right limits are the same, are not the same. All right, another method to find limits is called the squeeze theorem. In a squeeze theorem, we got 3 functions, and one of them is stuck between the other 2. In some open interval that has a in it, so here's an open interval that has a. So in this open interval, these 3 functions behave this way, such that the g is stuck between f and h. So if x approaches a and h and f approach, let's say, limit L, then g has no place but approach L. Has no other choice because it's stuck between the 2. And you see a picture of it here. So the green one is g, and here is f and h. So the green one is stuck between the 2, and when we get to this point a, these 2 functions, they approach that number right there, and the green has no choice but approach the same number. That's the idea with squeeze theorem. Let's look at an example. Now, what's the limit of x times cosine x? Well, we can use the limit law because we don't know what cosine of 0 is. The limit of cosine, we haven't talked about that. So what do? We're going to talk about squeeze theorem. So we know that cosine is stuck between -1 and 1, right? You know that from unit circle, that we know cosine is between -1 and 1, right? So if you have a function here, you have an angle here, cosine is that much. If it's over here, cosine is that much, right? So cosine goes from -1 to 1. Now, what about x times cosine? Well, we can multiply by x. If it's positive, we get this. If it's negative, we have to switch the direction of the inequality if it's negative. But we end up with what? We end up with this idea that x cosine x is between negative absolute value of x and absolute value of x. Right? Now, if you download and install this program in your computer, which is called GeoGebra, and is linked in Start Here page, you can actually graph these. Y equals to x times cosine x, like that, and then y equals to absolute value of x, and then y equals to negative absolute value of x, there. And then zoom out, you see that the green graph stuck between the red and the blue one. So as you approach 0 from right and from left, right, what happens to the function values on the green one? They approach 0, even though they fluctuate, right? But they approach what? They approach 0. And that's the idea. Okay? So this limit is based on a squeeze theorem equals to what we just found. Now, what about limit of sine when theta approaches 0? Well, remember, sine is not like other functions, because sine and cosine, they fluctuate, they go up and down, right? So when you want to approach a number, it's kind of tricky with sine and cosine. They go up and down, they don't approach something at some number. So they go up and down as you go around to different angles. So what we want to do is we want to prove what the limit is here. So what's the limit of sine? Now, on unit circle, we know that the radius is 1 here, right? Because it's unit circle. And on unit circle, the arc length is given by the general formula is r times theta. And since r is 1, then the arc length on unit circle equals to the angle. So if you have an angle of theta here, the arc length across from the angle is the same as the angle, the measure of it in radian, right? So the arc length is theta, and here is sine theta. Isn't that the sine theta? Yes, that length is sine theta. So notice that sine theta is stuck between 0. If the angle is 0, then the sine theta goes down. So it's between 0 and if you increase the angle gets bigger and bigger, so the arc length gets bigger. So sine theta is stuck between these two functions, 0 and theta. Now what happens when theta approaches 0 from right, this way, from right? Well, the 0 and theta have no place to go. They have to approach 0 and 0. So if these two go to 0, sine theta goes to 0. So from the right, we know that happens. Now, what about from the left? What if it's over here and we are approaching 0 from the left? Well, now we have negative theta, and then negative theta here, and then we have sine negative theta. Now we know sine negative theta is going to be between 0 and negative theta again, right? Because sine would be what? Sine negative theta is that much. And again, that's between this length, which is going to be negative theta, and 0 as you approach it, right? As I approach 0 from here, from negative numbers, that's what happens. Okay, now what is sine of negative theta? Sine of negative theta is negative sine theta, right? Because on unit circle, if this is the theta, the sine theta is that much, and if you have negative theta, then sine theta is that much, which means they're opposites. So sine negative theta is negative sine theta. So if you substitute that, and then multiply everything by negative, you end up with the same expression that we had before, right? And again, the same thing is true. So we prove that whether you go from right or from left, you end up with the same value, 0, right? From left or from right. So that means the limit of sine is 0 when theta approaches 0. So we prove that limit of sine when theta approaches 0 is actually 0. What about cosine? Well, we don't have to really prove it because, I mean, the same way that we prove sine. Because we know sine and cosine are related, right? How are they related? This way. So we can take, if we want cosine in terms of sine, just move the sine squared to the other side. So cosine squared is 1 minus sine squared. So cosine is plus and minus square root of 1 minus sine squared. But remember, we are trying to go to the left and right of theta. So that means we're staying what? We're staying in this region. If this is theta, you go to the left or right of theta, negative theta and positive theta if it's x, if theta is 0, approaches 0. We go to the left and right of 0. So this is 0, angle 0, this is positive angle, this is negative angle, right? So we are staying in this region, and if you stay in this region, cosine is always positive. So we don't need the negative one. So the limit of cosine is the limit of the square root of 1 minus sine squared, and we already know sine squared, the limit of sine is 0, so that's 0. So the answer is 1. So we just proved that limit of cosine when theta approaches 0 is 1. All right, what about this structure, sine over theta? If we use substitution, we can use limit laws, but it doesn't work because sine of 0 is 0 and this is 0. 0 over 0 again doesn't work. How do we do this? Well, we can prove it with a similar kind of structure here on unit circle. And we know that this distance here is sine theta. We talked about that already. We know the arc length is theta. Now, if you extend this terminal side of the angle until it hits this side right here, you know this distance is tangent. Why? Because the definition of tangent is what? Opposite over adjacent, and an adjacent here is 1 because it's unit circle. So this side is actually tangent. So tangent over 1 is tangent. So here we can say that theta, right, which is the arc length here, is between sine theta and tangent theta. Because obviously that arc is bigger than sine and is smaller than that. So we start with this right here. This is squeezed between these two. And then we divide everything by sine, right? Because we're trying to get this structure here. So we divide everything by sine. Sine over sine is 1. Tangent over sine is 1 over cosine, because tangent is sine over cosine, right? And then theta over sine is just theta over sine. Now, to get this, we can flip all sides, flip all three sides, and we get this structure, right? We have to, when you flip it, you have to change the direction of inequalities, and if you do that, you get this, right? 1 comes on this side, and this cosine goes on the other side. So we know that this structure is squeezed between cosine and 1, but what is the limit of cosine when theta approaches 0 from right or from left? Is 1. We can also similarly do the left one on the other side, right? But we get the same result. So that means that by squeeze theorem, we prove that the limit of sine theta over theta equals to 1 when theta approaches 0. In fact, not only that, but also the limit of sine of something, whatever that structure is, divided by that structure, when that structure goes to 0, is 1, right? That means, for example, what's sine of 6 theta divided by 6 theta when theta approaches 0? When theta approaches 0, then 6 theta approaches 0, and when that happens, the answer is 1. How do we know that? Because we just proved it, right? All right. Another structure that we're going to use later in calculus in order to prove formulas for derivative of trig functions is this one. So cosine of theta minus 1 over theta. To prove this theorem, to prove this limit, we just need to use a trick that we already know, which is conjugate. So we're going to take cosine of theta plus 1 and multiply the numerator and denominator by that. So in the numerator, we got again a minus b times a plus b structure. So we're going to end up with a squared minus b squared. A is cosine and b is 1. And cosine squared minus 1 is negative sine squared from this identity, right? If you move the 1 to this side and move the sine to the other side, that's what you get. So this is structure here, numerator, equals to negative sine squared. And the denominator, we're going to leave it the way it is. Now, what do we do with this? Well, the trick is to write sine squared as sine times sine, and then take the one of the positive signs and theta together, and then put the negative sign with this structure together, right? Like I did here. Now, this is the product of two limits. We can use the limit law. Limit of sine theta over theta when theta goes to 0 is 1. Limit of this, we can just substitute. Sine is 0, cosine is 1, 1 plus 1 is 2, 0 over 2 is 0, so 0 times 1, 0. So the limit of cosine of something minus 1 over that something when that something goes to 0 is 0. That is very useful later on in chapter 3. All right, so what is that? Well, if we substitute, it doesn't work. Again, we get 0 over 0. How do we do it? Well, we can write tangent as sine over cosine, and then simplify it to just cosine, and the answer is negative 1, right? What about this one? Well, this one doesn't look like sine of something over something, but what if we make it look like that? What if I put a 5 here? That we don't know how to do it. That's just 1. But I can't just put a 5 here. I have to put a 5 here too to compensate for that. But then that's the answer, right? We can write it as 5 times that. And this we know is 1. So 5 times 1 is 5. All right. It says show that this limit does not exist. How do we do that? Well, we know that this is a piecewise function. So absolute value of x over x is really a piecewise function. It is x over x when x is greater than or equal to 0, but I don't put equal to because the denominator cannot be 0. And it is negative x over x when x is less than. So basically it means this function is just 1 when x is greater than 0, and is negative 1 when x is less than 0. Right? And that's it. So the left limit is negative 1, the right limit is 1. And they're not equal, right? So that means this limit does not exist. Okay? Now I'm going to make another video to talk about the rest of the chapter. So I'm going to come back here and say bye to you until next time. Take care of yourself and each other. And, I see you in the next video.